Okay, welcome again to our discussion about the atomic structure. In this part we look at the electrons, no longer at the nucleus and the mass of atoms. Okay, how about the electrons? In the earliest model, which is scientifically based, that is the Bohr model from Mr. Bohr in Denmark, who developed this model 100 years ago. He said every positive charge in the nucleus corresponds to an electron with a negative charge, and this electron circles around this nucleus, similar the Earth circles around the Sun. Now, he made the following interesting experimental observation. When he looked at the hydrogen gas, he made like an electric lamp, and in this lamp we have hydrogen gas, and then he put a high voltage into this lamp, similar our so-called neon lamps, and then at a certain voltage suddenly the gas starts to give a light, and mainly for hydrogen is a very blue light that he got. Okay, and now we can analyze this light when we separate the different wavelengths in a prism, and then we record the different wavelengths that we get from this light on a film. And now interesting, when we look at the light from the sun, we make this experiment, then we get like a rainbow color. We get a continuous spectrum from red to blue, similar in the rainbow that you see. But the light from this gas is not continuous. It has certain lines in the spectrum, and the rest is dark. So that means, and we have here wavelength lambda, that means that the hydrogen gas only emits light with certain energies, because every wavelength here corresponds to an energy. And we should remember this Planck's formula between the energy and the wavelength of a electromagnetic wave, like light. The energy is h times c, is the constant, divided by lambda. So every wavelength we get here corresponds to an energy. So Mr. Bohr thought, oh wow, where come these certain energies, where do they come from? And he developed a model in which he said, okay, what happens when I bombard this atom, hydrogen atom, one proton, one electron, when I bombard this with other electrons from the electric, like an electric spark. When this happens, he said, okay, then the electron in the atoms, when they get hit by one of these, they can jump up to another orbit. So let's say this is orbit number 1, this is orbit number 2. That means it absorbs energy that corresponds to the energy difference between these two orbits, and soon after that the electron will go back to its original position, and when it goes back to its original position it will emit light with a certain energy. And there are not only two orbits, because if there are only two orbits we would have only one line in the spectrum. But since we could have many orbits, 3, 4, etc., an electron could go as well 2 steps up one down, one down, and every time it goes down, it will emit. So here the same as before. Or it will go from here to here, emit. So in this model, we can imagine that the electron can live only in certain orbits. It cannot be in between, because from the line spectrum, the emission spectrum we see, we get only certain energies that come out from the atom. And this is typical for every atom, sorry. If you put like the helium gas, you get different line spectrum. If you get a sodium gas into this lamp, you get different lines. That means every atom has typical orbits for its electrons. This information we can now make like an energy diagram for the electrons, for example first in the hydrogen atom. We can say, okay, in the ground state, the electron is on the lowest level, and we just name this orbit number 1. If we put energy in this electron, it will jump to the next level, n equal 2. If we put more energy, it will go to n equal 3, n equal 4, and so on. And we can find that the distance, energy distance between these levels becomes smaller and smaller the higher we get, the closer these levels come together. In the extreme case, the electron can go out completely from the atom and just become separated from the atom, and this energy is the ionization energy, which produces the H ion. And this ionization energy we can measure is 13.6 electron volt for 1 electron. So if we put this energy, 13.6 electron volt, into 1 electron, it will leave the atom and cannot come back. So electron volt is a funny energy unit that we use mostly in spectroscopy or when we look at single atoms. 1 electron volt is the energy that an electron, 1 electron gets if we put it in a charge 1 volt, therefore the electron volt, plus minus, over a distance from 1 meter. So if you put an electron and accelerate the electron from plus to minus in a charge of 1 volt over 1 meter, the electron will have the energy of 1 electron volt. And this energy corresponds to wavelength. 1 electron volt is about 8,000 centimeter minus 1. We remember 8,000 centimeter power minus 1 is the nu bar, is the wave number, which itself corresponds to the wavelength of the light. Okay, so now we can find out the energy levels for all these orbits until the electron completely leaves the atom, and we can even develop a formula that these energy levels are exactly this 13.6 electron volts, 1 over n1. One level is the level where the electron will come down, minus 1 over n2 square. Okay, sorry. So this is Rydberg formula. With this simple formula we can calculate the energy of light that comes out when 1 electron goes from level n2 down to a level n1. The energy it emits and with this formula we can calculate the wavelength that we will get from this transition. Okay, simple example. We look at the transition between the level n equal 3 and n equal 2. So one electron goes from level 3 to level 2. What is the wavelength of the light that will come out? So we use our formula here. The energy is this magic number 13.6 electron volt multiplied by 1 over n1 is 2, so 2 square minus 1 over n2, 3 square. And this is 1 over 4 minus 1 over 9. And if we look at this, we will get something like 1.889 electron volt. This is the energy difference between level 3 and 2. And now which wavelength corresponds to this energy? So we know that 1 electron volt is about 1000 centimeter minus 1. So that means the 1.889 electron volt multiplied by 8000 centimeter minus power 1 gives us something like 15,100. Oh, sorry. Centimeter minus 1 as the wave number. And the wave number is not so nice to imagine. We want to have the wavelength, so we know lambda is the reciproc of wavelength, but in nanometers. So that means 1 divided by 1000, 15,100 centimeter, and centimeter we should replace with nanometer. 1 centimeter is 10 power 7 nanometer. And if you check this out, you will get about 660 nanometer as the wavelength. So this is the visible region. So from this calculation we can calculate the energy difference between every level, and we can calculate the wavelength that we should give and compare it with the experimental result, and this is in quite good agreement with each other. So this model works very well for hydrogen. Okay, you think now this is good and well, but unfortunately we are not finished, because there are something we cannot explain. First thing we cannot explain, in the spectrum, when we look closely, very closely into the spectrum, we find the line that we get from N3 to N2. This is not a single line in the spectrum, but when we look very closely, we find is a double line, very close together. So this is one thing, we call this fine structure. And many other lines appear as multiple lines, not just a single line. So this fine structure we cannot explain with this model here. Second thing, we cannot explain why the electron would stay on certain orbits. Because there is, from the classical physics, there is no reason why the electron have a certain distance. And especially from classical physics, when we have an electric charge that accelerates, like in a circular motion, it will emit energy. That means an electron rotating around a nucleus in this manner will lose energy, and eventually it will fall down into the nucleus. It cannot be stable in this situation when we look at classical physics. So this is an even bigger mystery that will be solved in the next clip that I will give you. Then now part number 3. Please don't miss it. Thank you very much and see you later.